Hello, welcome to the course Electronic System Design. Last lecture we were discussing about some PCB issues when we fabricate or when we design these PCBs for fabrication. What are the common issues what we face as a designer when we have certain schematic which we want to implement in PCB? Those are the issues generally come while designing the PCB. So last time we saw that the major issue when we design these PCB, or especially the high speed designs for the PCB, because the low speed designs do not need much of a care for these issues. However, most of our designs, when we design these PCB, most of the PCBs, they fall in the high speed category. So these high speed designs need special care, and we saw that some of the issues which are generally come is, first is the impedance mismatch. When we have a trace on the PCB, when we design it, so we design it for a particular width and signal flows in those traces. Then if there is any change in the physical dimension of this trace, or there is any other component which is connected to this PCB, that interface acts as a impedance mismatch, and if there is a impedance mismatch, that acts as a interface where the signal will bounce back. So when the signal is propagating, let's say positive x direction, and we have certain impedance mismatch, it will be bouncing back from that and will go into the negative x direction. However, when we have negative x direction movement of this reflected signal, this will go to the original site where we are feeding this signal. That site also acts like a interface, because that time we have a signal generator which is putting the signal on the trace. That additional component is connected to that trace, so there also it will bounce back, because this also acts like a impedance discontinuity or impedance mismatch. So this reflected signal which is traveling in minus x direction, it will bounce back again, come to the positive x direction, and this cycle follows. It will bounce back again, go into minus x, bounce again into positive x. So because of these multiple reflections, we encounter certain phenomena which is something called ringing. As we discussed last time, we have a proper signal, and because of this back and forth movement of waves, which is nothing but the electrical voltage, this voltage gets superimposed on the signal, and this signal will now see certain amount of ripples in its level. So it's not a pure signal now. For example, if we are sending a 5 volt, this 5 volt is superimposed by this back and forth movement of voltage, and this 5 volt will be ringing between 4.9 and 5.1, for example. So there will be a ripple on the signal, which is undesirable, and the typical case or the more critical case of this ringing is overshoots and undershoot. If we have so much of reflection at the interface, this will cause a overshoot in the signal, or undershoot. If it is positive, then overshoot; if it is negative, then undershoot. Both are bad actually for the electronics, because if it is a overshoot on the positive side, so this 5 volt becomes typically, let's say, 6 volt or 7 volt. Our next electronics, this may not be kind of tolerant to this high voltage stress. 5 volt means the electronics is safe for 5 volt operation. However, if the 7 volt comes at the next circuitry, which is typically the gate of some MOSFET, this MOSFET can get damaged because of this extra voltage from 5 to 7 volt. On the lower side, when the voltage is decreasing, for example, the minimum voltage is expected 0 volt. However, because of the undershoot, the voltage goes below 0 volt to, let's say, minus 2 volt or something. This voltage might be going to some drain of the transistor or some other circuitry. The drain is typically a diode, which is, let's say, PN diode, which should be in the reverse biased always, so that it's not burning any current. However, because of this undershoot, Now that diode may get turned on. This causes a reliability issue where this diode is turning on, pumping a current maybe from the substrate to this node. So this is very highly undesirable. So these voltages overshoot and undershoot both are undesirable. So this is very typical issue which comes during high speed PCB design. Next issue what we are going to discuss today is something called crosstalk. Crosstalk is something when we have two traces, both are carrying signal. So this trace, which is, let's say, carrying the signal, and the adjacent trace, these two traces have some amount of coupling when they are running parallelly. Whatever substrate we have in between, it may be air, it may be some other material. Because of that, these two traces are having certain amount of capacitance, and these two metallic traces act like a metallic plate of a capacitor. In between whatever we have, that act like a dielectric. So because of this capacitance, one signal is switching, let's say, at high speed. This voltage will be coupled to the another trace, and that trace will also see the effect of having this signal switching at the very high speed. So this produces something called crosstalk. This is also induced voltage which is undesirable because the next trace might be carrying a slow moving signal. That slow moving signal will see a high speed signal coupled to this slow moving signal. This will also see some kind of ripple in the output voltage. So let's see what a crosstalk look like. So the crosstalk occurs when energy is coupled from the aggressor signal, which is the, let's say, the fast moving signal, to the victim signal, which is facing this extra voltage due to this mutual coupling. From the aggressor, signal to the victim signal. This happens due to the interference of electric and magnetic field. So for example, we have a aggressor track. Let's say this is our aggressor. So this wire is carrying a voltage. So now the point is, this aggressor is carrying a time varying signal. If it is carrying a DC signal, then there is no electric or magnetic field developed, then there will not be any crosstalk between these two traces. So this is aggressor, this is victim. So if the signal is DC, or we are just having a very slow moving signals in few hertz or some lower kilohertz signal, then there will not be much crosstalk between this aggressor and victim. However, if the signal is very fast moving or the rate of change is very fast in the aggressor, this is going to produce some electric and magnetic field along its length. So this is the entire length we have, and across this there will be electric and magnetic field developed. If there is another track, this victim is close by, then this induced electric and magnetic field will produce some voltage or some noise on this victim. That depends on how fast the signal is moving. If the signal is moving very fast, then there will be a lot of crosstalk induced on this victim. So this is the crosstalk which happens because of the time varying signal. So the techniques let's discuss to decrease this crosstalk, which we generally encounter in PCB design. So the very first intuitive solution for reducing crosstalk is we increase the distance between these two tracks. So this aggressor, this victim, this aggressor is producing this electric and magnetic field which is very much high, very close to this aggressor, and it decreases the strength exponentially while going away from the aggressor. So if we have a large distance between aggressor and victim, then the effect of aggressor on the victim will be very less. However, because of that, it needs much area on the PCB, because we this extra space we need to put between these lines, which is not very desirable design approach because it increases the size of PCB. So the first technique is increase the spacing. Between signal lines as much as possible. The energy in the space is reduced significantly with the distance. The next solution to reduce the crosstalk is when designing the transmission line, the conductors, these two traces, should be placed as close as possible to the ground plane, which will terminate all these field lines to the ground, and there will be less effect on the victim. So, the other technique is the conductor or the trace should be placed as close to the ground as possible. The third technique, which is also very much followed, is implement different routing techniques wherever possible. For example, that in one layer, if the track is running in perpendicular direction, the in the other plane or nearby traces, those other traces should be run in parallel or horizontal manner. So, implement different routing techniques. Wherever possible. One other technique is to route the signals into different layers. And other technique is reduce parallel run lengths between signals. So, these are some techniques to reduce the crosstalk. The very first one is, which is very obvious one, is if there is a coupling between these two traces, one is fast moving, one is slow. So, we can increase the spacing between these two traces so that the coupling reduces. However, if we increase this space, this is going to increase the area of our PCB design, which is not very good technique to reduce this crosstalk. The second one is we run the trace and put the ground plane very close to this trace. For example, in the bottom layer we implement the ground plane, or very next to this PCB we fill all the whatever area we have, that we can fill that with the ground connection or the ground plane. In this case, if there is an electric or magnetic field developed, that will be terminated to that ground plane, and with this will not reach to the next trace, which can be a victim of this high speed signal. So putting this ground plane close to the high speed signals is one idea where we can reduce this crosstalk. The other technique is we do different routing techniques wherever possible. So when this trace is running, because of this high speed signal, there is going to be electric and magnetic field developed across the line of this trace. If we have another trace which is running close to this through the entire length of this trace, that will receive much more coupling if it is running very parallel to this trace. However, if we have this aggressor line which is running, let us say, in x direction, so all the magnetic field will be along this line. If we route our other trace or other signal perpendicular to this line, then for a very small amount of area there will be a coupling between this aggressor and the victim. So because of this routing style, which is now perpendicular to the aggressor, we have less amount of crosstalk between aggressor and victim because of the different routing style. So that we can implement. Another technique is the signal should be routed in different layers. So if you have possibility of multi-layer PCB, so there are multiple layers you can design. You can try to put different signals in different layers so that there is less coupling between these two traces. If traces are in the same layer, there will be much more crosstalk. If we change the layer itself, the other layer comes below that the first layer, then there will be less crosstalk and we can reduce this problem. The other one is reduce parallel run length. So as we discussed, these two traces should not be running in parallel. You can have some angles or some separation between these two traces to reduce this crosstalk. So this crosstalk is very challenging issue when we design these high speed PCBs. The next issue which frequently comes in is called via stub. So in via stub, what we have, when the signal is propagating and we need to route this signal into another layer, which is very frequently the case because all the signal we cannot have only in one top layer or the bottom layer. We have to change the layer from top to bottom or to intermediate layers. That time we need to use something called via. Via is kind of a hole in the PCB which takes the signal from top to the intermediate or the lower levels or lower layers. This via, when we make these vias, extra amount of length of this via which is connected to the signal, this act like a stub. Stub is something like a extra piece of conductor which is connected to your main conductor, and this acts like a stub, or in for high speed designs or high frequency signals, this extra piece of metal act like a small antenna sort of thing. In the RF electromagnetic designs, you can study what a stub actually called in. So this stub actually comes in when we put a via to connect two conductors. This extra amount of length act like a stub and we call it the via stub. So let's discuss that what is a via stub. So when a routed signal starts from the top layer and ends with some inner layer or the very bottom layer, the remaining portion from the inner layer to the bottom layer is called a via stub. When a routed signal starts from the top layer and ends with some inner layer, the remaining portion form the inner layer to the bottom layer is a via stub. So for example, in this diagram we have one trace which is, let's say, on the top layer. So this is our top layer. From top layer the signal is going this direction, and because of many constraints we want to take this signal into some other layer. For example, in between we have layer 2 and layer 3. So from the top layer we want to take this signal into another layer, and this layer is, let's say, layer, let's say, 1. So to do this we need to put a hole in the PCB layer from top to this intermediate layer, and we fill it with copper so that it is conductive. So the signal from the top layer, it travels through this via and goes to this layer 1. So this is how we route the signal from top layer to some intermediate layer. However, when we make these holes, this is through hole from the top layer all the way to the bottom layer in the whole PCB. So this is, let's say, our bottom layer. So this extra piece of metal or extra piece of via which is unused here, the signal only needs from top layer to this layer 1. However, this extra piece of this stub or this via which is there from this layer to the bottom layer, this act like a stub, and this causes problem when the high speed signal is going from top to the layer 1. So this act like a via stub. So the next issue which we can discuss is skew and jitter. So let's write what is skew and jitter. So the next issue which also comes very frequently in high speed design is skew and jitter. These are very important issues because when we talk about high speed signals, generally our assumption is for the low speed signal is that when we apply a certain input at one end of the trace, that signal reaches to the other end in almost no time. However, in practice, when we apply certain signal at one trace, which is let us say a few inches long, this signal takes some amount of time, which is finite number. This much time is taken by this signal in reaching from the input to the output, or the one end of the trace which we call near end to the far end of the trace. This number is finite, it takes certain amount of time, and this time is proportional to the length of the trace. The longer the length of the trace, it takes more time in reaching from near end to far end. So this creates problem when we designing some synchronous circuits. For example, we have high speed circuit where we are expecting two signals to come at the same time. So let's say we are synchronizing two blocks using a single clock, which is our universal clock. Now the delay depends on the length of trace. So now we have two blocks which should receive the signal exactly at same time. However, we place one module or one block very close to the source and one block is very far away from the source. Now the first block will receive signal much earlier than the another block. This causes the problem of time skews. These two are not getting the signal exactly at the same time because of the difference in the length of the traces. They are receiving the signal at different time instances. That is called the time skew, or simply the skew in the timing of the signal. So this problem comes very frequently in high speed designs, and we need to minimize, or we need to kind of put the equal length of the trace where we want to have this kind of synchronization. So let's discuss what is skew and jitter. So the point we need to note is the signals take finite time as they travel on a PCB. From source to receiver. The next point is the signal delays are proportional to signal line lengths. So because of these phenomena, if the data signal and clock signals do not match in overall delays, they will arrive at the different time for the detection at the receiver. This would cause the signal skews. So if data signal and clock signals do not match in overall delays, they will arrive at different times at the receiver. This would cause signal skews. This delay actually depends on multiple factors, not only on the PCB trace length. This also depends on how much parasitic capacitance we have with this trace or other kind of issues. So if there is any difference in reaching this signal at different lengths at the receiver, this would cause the signal skews. Let's take one example. So let's say we have this signal which we are applying here. So these dotted lines are the expected time where our signal should come in. However, this is the far end signal which is shown here, this black curve, and then this goes down at this specific time. So ideally we expect we send a kind of squarish signal, this pulse with almost zero rise and fall time. However, it is not possible. We send this practical signal with certain rise and fall time, and because of multiple factors we get this kind of signal which is shown here by this black and red curve. At the corners it has certain amount of rounding. This is because of the RC effect. So first thing, we have this rounding at the sharp edges. The next is this fall is not exactly at the same point all the time. For example, here we have this fall. Let's say I'm showing it by red curve. It means it has little bit more delay compared to here where this fall is shown in green. Here this fall is relatively sooner compared to this red curve. This happens because of multiple factors, maybe let's say parasitics. There are multiple factors which can cause this type of thing. So the point is, on the corners, on the sharp edges, we have this rounding, and other thing is we have, for the same falling edge, we have different numbers of delays. Here we have, let's say, the delay is lesser, here we have, let's say, delay is longer. Similarly, for the rising edge, let's say here the delay is smaller, here the delay is higher for the same rising edge. We have one rise here and one rise here in this signal, and both having different delays. These TPLH is different, let's say TPLH1, and here we have TPLH2. These two are different. So these are the issues which we want to encounter. This causes the signal skews. So how do we calculate or how do we quantify the skew for the measurement? So what we do, we take this full waveform. When we simulate this circuit, we take this complete waveform and fold it something like this. For example, this is our folding cycle. We take this complete waveform and we kind of take this as a T monitor. This is the time where we want to monitor, and at this point we fold this signal from here to here. This is another instance. Let's say this is 1, this is 2, this is 3, this is 4, and this is 5. We take these time instances, put on top of each other. This is 1, we overlap this 1 with 2, with 3, with 4, with 5. If we overlap these things, we get this type of waveform. This is our black curve from the first frame. Then we have this red going down. This is from the second frame, this red goes down here. So this is from this red from the second curve, this is green is from the third one, and so on. So when we superimpose all these frames together, we get this type of waveform. This we call it the jitter waveform or the eye diagram sometime. So in this eye diagram, we can monitor multiple things. For example, if this rounding is very high for multiple cycles, we need to remember that we are simulating or we are measuring this delays for large number of cycles. For example, 1000 cycles we are superimposing. So for all the 1000 values, we'll have different waveforms that will tell us what is the worst case and the best case delays here. So this is the delay. What is the best and worst case delay? If these waveforms take too much of space, this opening or this white space here, this decreases. That we can say the eye of the diagram. This eye window will shrink if we have so much of or the large number of variation in the delays. Similarly, if we have more rounding here, then also our opening of the eye will decrease. This we can see in another example. For example, this is a good design where if we measure the delay by these black arrows, this is the overall delay. we have, which is very closely packed. They are not very different, and rise fall are also relatively better. So we have so much of area of the eye which is open. This area, or we called opening of the eye, this area is very much larger. However, this is a bad design, or we can say for the high speed design, where we have the eye opening is very small, and we see the rise and fall delays are not very equal. This is the rise and fall delay difference in the best case and the worst case. So all the things we can measure using one single eye diagram. We just look at the opening of the eye. If the opening of the eye is less, it means we have delays which are impacting our design, and which we have the supply or these RC charging and discharging, that is causing problem to our design. So with a single waveform which is called eye diagram, we can calculate so many problems that our high speed design is facing. So this diagram is called eye diagram, and this is called the jitter in the timing waveform. This can be improved by trace length matching. So this jitter can be minimized by trace length matching. So this is very important parameter which we monitor in high speed designs is skews. And how do we quantify the skew? That is done by the eye diagram, and we measure the jitter, which is the least possible delay and the best and the worst possible delay. Those numbers that we call the jitter numbers, these numbers should be smaller, and this visually we can see in the eye diagram. When we plot the eye diagram, if the opening of eye is very small, it means either the signal is very high, or our electronic or our hardware is not able to support that signal which is on the higher side. If we have larger opening, in the first case we have very good opening of the eye, it means the signal is either slow moving or our hardware is fast enough to support that high speed signal. So for a good design we should have a very good opening, and as the signal increases, the frequency of operation increases, the eye diagram, the opening of eye becomes smaller and smaller. So this is very important parameter which we often design our PCB to meet skew numbers or the jitter numbers. The next issue which frequently comes in the PCB design is signal attenuation. What is a signal attenuation? When we apply a signal on a trace and it travels from near end to far end, these metal traces, they are of course some metal, let's say copper we are using. All the metals has certain amount of resistance. So when we apply the signal which is traveling throughout the length of this trace, because of the resistive nature, this signal will attenuate. The strength of the signal goes down, and this strength of the signal not only depends on the resistance, but also it depends on which layer we are sending this signal. So this signal, this gets impacted by the resistance of the wire, as well as how many discontinuities we have throughout the length from the near end to far end. Let's see what this is. Signal attenuation. So the signals suffer attenuation as they propagate over PCB lines. This happens due to losses caused by conducting traces. And this loss is also caused by dielectric dissipation factor. So because of this resistive nature of the line, there is a loss, as well as the PCB material has certain dielectric dissipation factor. Because of that also there will be some amount of loss in the PCB material. Both of these losses increase with the frequency. Therefore, high frequency component of the signal will suffer higher attenuation. So the loss actually increases with signal frequency. Here is one graph which is showing the loss which is on the y axis. This loss actually increases as the frequency is increases on the x axis. We see the graph is from 1 gigahertz and above. So when frequency is increasing, there is a consistent increase in the loss. However, we have different losses. These are because of the different material we use. So for example, one graph is for the 370 HR, which is one grade of PCB. Then we have some other materials. There are so many materials available in the market to manufacture the PCB, and the loss depends on what material we choose. But in all the materials, the loss is actually increases with frequency. So we need to choose the right type of PCB material. For high speed designs. So this is one technique to reduce the signal attenuation. So here we have another important issue which comes in high speed design is signal attenuation. And as we said, the signal actually suffers attenuation when we send from the near end to far end. This attenuation happens because of the resistive nature of the material, copper or aluminum, whatever trace material we choose. There has a certain amount of resistance. That resistance actually degrades the voltage or the signal value. And the other cause of this attenuation is the dissipation factor inside the PCB material. So the PCB material, for example, we are taking FR4 substrate. So FR4 has certain dielectric dissipation factor DF. Based on that, there is a dissipation in the material itself with the frequency, as we see on this graph. If we increase the frequency of signal, the dissipation, the loss actually increases. Now this brings us very important point that let's say we are designing a digital PCB. The signal we want to send is a pulse signal from the near end to far end. However, if we remember from the Fourier series, this square pulse is actually composed of so many sine waves, sine or cosine waves. So this rise and fall which are very sharp in the square pulse, these are implemented with nothing but the sine waves. Sine waves are from very low frequency to very high frequencies. We are using, for example, 100 sine waves to implement this square pulse. These sine waves have different frequencies from low frequency to high frequency, and our attenuation, as we see here, this attenuation depends on the frequency of the signal. So when we are sending this square pulse, it means we are sending 100 sine waves of different frequencies. So low frequency sine waves will not suffer much of attenuation. However, the high frequency sine waves, they will suffer so much of attenuation. And at the far end, what we receive, that high frequency sine waves are little attenuated compared to the low frequency sine wave, and then we take all these 100 sine waves, combine them and see we want to convert it back into a square wave or square pulse. We will see, because of the less amount of high frequency sine waves, this square pulse is no more a square pulse. The high frequency components will be missing from these square pulses. High frequency components are generally important for rise and fall time, because this is the time where the signal is switching very fast from low to high. There is a very fast switching for square pulse. So these rise time where we need high frequency components, and fall time where we need again high frequency component for very fast switching, these are missing at the far end because of attenuation. So our rise time will be impacted and fall time will be impacted. So our square pulse, what we receive at the far end, will not be as good rise and fall time as we have transmitted at the near end. So because of the attenuation, and attenuation is dependent on the frequency, we have the degradation in rise and fall time. So these are some issues what we face by designing the high speed PCBs. These are very often comes because most of the time we design high speed PCBs or even RF PCBs which are on the very extreme side of high speed PCBs. In RF PCBs we use very high speed signals, and the time of flight from near end to far end is very much comparable to their transit time or TPLH, TPHL. So RF PCBs are very complex PCB designs which we encounter, but in high speed PCBs or digital high speed PCBs, these are some of the issues which we generally face during the design phase. So this is all for today. Thank you.